So we directly continue. There's already Bharat Agarwal from National Instruments. So as you can see, National Instruments has been bought by Emerson. But National Instruments is well known for the USRPs, but I believe Bharat is from an office in Dresden in Germany that also does a lot of use cases around the USRPs and also OAI, and he will talk from ORU to the Sky, Proto-ORU, X420 and NTN.
Thank you, Robert. Thank you. Yeah, sure. Okay, hi, good morning, everyone. My name is Bharat Agarwal. I work as a 6G wireless application engineer in Emerson NI, based in Dresden, Germany. It's good to see that there's a lot of USRPs and SDRs on the demo, so good to see that. Just a small introduction about me, what areas I work in. So I work in mostly in NTN and ISEC stuff, and following a lot of 3GPP meetings in Malta, in Singapore, and now in Maastricht, also in Netherlands. I've been working with OAI from like past 5 years now. Back in 2021, I started working as an intern in NI, doing my PhD times, and now I've been working as a full-time employee in NI, and again, still working on OAI stuff. So let me address the elephant in the room right now, the USRP X420. So we have a new USRP which is ahead of X410. So this is a wide bandwidth. You also get the LO sharing and the high frequency coverage, specifically for the FR3, KU band and X bands. So those who works in NTN, they would be quite excited to see this particular stuff for them. So this is how it looks like, exactly similar like for the X410, not much change in the picture, but it has a less number of channels, so I will come to that point. So if you see in the terms of technical specifications, so the frequency range is something very interesting to look into it, that it can goes up to like 20 gigahertz of the frequency, and then the bandwidth of each channel is up to like 1 gigahertz. The number of channels is 2 transmit and 2 receive. We have an onboard GPS DO, and also for the BPS and the LO in and LO out. You can control to the HDMI GPIO interface. We basically use this type of GPIO interface in some of our internal research that we do for controlling some of the antenna elements. Again, you can do it with OAI also. You can integrate the OAI to control the antenna elements. We have an FPGA on board, and the interface is 10 gig, 100 gigs, and also as well as 10 gig via QSFP828 cable. In terms of software specification, as you know that you can use the open source softwares like UHD, GNU Radio to control the USRP, but you can also use the RF NOC if you are interested in the FPGA development of the USRP. So now the bottom line is that why should we choose this particular piece of an hardware? So it can help you in prototyping the radar satellite communication, also on the NTN for the 6G frequencies up to like 20 gigahertz. It creates a multi-channel phase coherent. So if anyone who is interested in MIMO stuff, you get the phase coherent channels with an built-in LO sharing capabilities with less than 1 degree of an RMS. You can process the data in real time with a large onboard FPGA. So right now Raymond was talking about ISEC thing. So if you are interested in having an IQ samples on board and want to have some things, you can use those things. You can sync multiple radios with built-in GPS DO and 10 megahertz PPS in and out. The open source UHD drivers can let you choose to work on this thing. So yeah. So we showed this demo based on X420 and ICC last month in Glasgow. So it's a very basic demo that we try to show and show the capabilities of a USRP that we are transmitting at 11 gigahertz. A signal. So we generate a GNU Radio flow graph in the Jetson, and then we upload it on the X420, and we transmit the signal, and then we receive it on the DVB-S2 receiver, and then we just simply show that okay, you can transmit a signal at 11 gigahertz. You don't need any up converters and down converters for this thing, and this piece of equipment will transmit the signal at 11 gigahertz, right? Okay, now let me talk about something Proto-ORU. So maybe you have heard about this Proto-ORU and also see a demo from National University of Singapore. And as an NI, we are quite interested in this piece of thing. So why we are interested in this piece of thing, let me just talk about you. So let me just give you a little bit background around what is this Proto-ORU is all about. So it's based on an SRS RAN radio unit emulator. And it has extended 3 new capabilities to become a fully compliant ORU. So it's an open front haul interface, which is it do the packet processing for you, then low-fi processing, so physical layer processing function, and then also a UHD-based radio, so it can integrate with the SDR. So and if you see the Proto-ORU, it's a fully compliant software-based ORU. It's run on a general purpose processors. SDR is an RF front end, so no dedicated oscillators are required. So these are the two important things, that it's a general purpose processor, software-defined radio, and so you don't need much of the stuff. And what are the use cases that is enabled for you is like, you can do a most rapid prototyping, you can do the algorithm development, you can do the performance evaluation, ORAN experimentations. There's no end for doing these things when you have an open source ORU, and you can have your own IQ samples in the time domain. So let me talk more about this proto-ORU and try to take you that why we are talking about these things. So why should we use proto-ORU? That's one of the questions that can be asked, right? Just want to give you a heads up. Whatever I talked about previous in this slide, it is also compatible with OAI, right? So everything can work with OAI also in this slide. So we have an OAI core network, we have OAI CU, DU, and then we have an open source front hall, and then we have an ORU. So I put a black color in those things because it's a black box for us, because when we go and see all the commercial grade ORUs, they have fixed functions and proprietary, right? And now then I try to compare the proto ORU with the commercial grade ORUs and try to say what are the parameters can I compare those two pieces of equipments. So I try to understand, okay, how about usage? So yes, I know commercial ORUs can use for commercial deployment, but proto ORUs can be used for the research prototyping. In terms of duplexing mode, TDD or FDD, but proto-ORU gives you the freedom of, you can support your own duplexing modes. Frequency bands is limited in the commercial ORU, but you can support different frequency range depending upon the SDR. So here the SDR plays a key role. If your SDR is X420, you can go up to like 20 gigahertz also. AML-driven research is limited because you are not being exposed to all this, what is going inside the ORU, right? The I50 and F50 blocks and also the front hall interface. But you can do a lot of ML-driven low-fi processing here. Open front hall protocol designs, you cannot extend the open front hall protocol, but you can do the more exploration on the open front hall with this proto ORU stuff, right? So for an example, in ISEG, if I want more number of metadata to be get transmitted from the ORU to my XApp over the E3 interface, can I enhance my open front hall interface? Yes, you can do it by using the proto ORU, but a lot of good things comes with some drawbacks also, So timings are something which is having a huge drawback in the proto ORU. We know that all the commercial grade ORUs are being like standardized with ORAN compliance, but there's a limitation in the proto ORU in terms of an high end-to-end time and along with this. So just want to give you a heads up on where does the latency comes from and how does this adds up. So the largest contributor is because of the SRS run hard-coded or the OCODU hard-coded thing, which basically takes your 3 slots, 1.5 milliseconds of time. The another significant contributor is that you are doing every packet processing on CPU, so nothing GPU or no accelerators are used. So it takes a lot of time for you to do the processing of the downlink symbols that you get from the DU. The another contributor is the low-fi uplink processing. Again, everything is running on the general processor. And then I just conclude that thing that if you try to shift it from the general processor to the GPU or to the SX, then we can think about it that yes, we can reduce the latency in the order of some milliseconds, and that can be a good boost to some of the use cases that cannot be solved as of now. So again, you must be thinking, okay, why you guys are so interested in this thing? Because we showed this demo in ICC again this year in last month. So a very basic type of a test bed. We have a DU, we have an RU, and then we just simply connect the Quectel UE, and then it's they all are time synchronized using the PTP. So you can see the clock here. Now let me talk about NI channel emulator. So yes, we have a channel emulator in house, and what we call it as a chess. So it's called a channel emulator system software. What does it do for you? It's a real-time channel emulation. You can use the feature-based processing and a software IP to emulate your complex RF channel conditions. It's a VST-based thing, so it's a big PXI chassis in which you have multiple cards in it, and then you can use the big FPGA for it. It is easily configurable with using the Instrument Studio, so you can use the lab view to configure the channel emulator. And you can also support for the advanced RF testing for it. Right? Just let me take you to this example basically here that will basically give you an answer lot of the questions that you're thinking about right now. So if you see mostly on the left hand side of this is the real-time scenario, and that you have a ground station and then you want to communicate with a satellite. Can you create all this, emulate all these things in a simulation? Yes, you can do it by using the NIHS here. So you can basically provide line of sight, delay, Doppler, all those things, and then you can communicate with the chess. Then again, let me just more talk about chess here again. So you can test this thing against real-world scenarios. It's a simplified aerospace satellite testing. Now the question will be asking, okay, how should I talk to chess? So it's based on gRPC, right? So if you're aware about gRPC, then you can talk to the chess using the gRPC API. Now, so Instrument Studio is basically used to initially configure the channel emulator. Once you have configured the channel emulator, and if you want to talk it through MATLAB or through Shiona, any other software that you are interested in, you have to use the gRPC API, right? And yes, as I mentioned, it's a cross-platform compatibility, so it can work with MATLAB and all of the stuff, right? I have marked some of the key features in the green here, so just to highlight you that the frequency range can go from 30 megahertz to 26.5 gigahertz. We can have a channel bandwidth up to like 2 gigahertz. We have number of RF channels up to like 4 channels. Channel parameters is something which you will be interested in to know that you can have a gain path, delay, frequency shift, additive, white Gaussian noise, and you have a 32-tap filter in it, right? And you can program it with the gRPC-based API. So this is something which we are internal doing it right now. It's just an architecture that I want to present in front of you. If you want to discuss more about it, I'm very much open to it. So we have a TLE data, and we are using an open source software called ORCID to generate the satellite position, velocity, and the UE position. Then we are using an open source SIB19 generator to generate the SIB19 for us. And then this SIB19 value we also provide to OpenNT and Shiona, and then the Shiona upload this HDF file on the NIHS, and then we communicate over the NTN channel. These things. This still thing is on the theoretical side. A lot of discussion I had with Thomas yesterday and also today. We are looking into these things, and this is where we are using the capabilities of Shiona. If you guys want to collaborate with me on this particular project, I'm very much open to it. So this is something internally I'm doing right now, and we are going to extend it to multiple open source softwares, right? Yeah, thank you, Ricardo. Yes.
I have a question to the. Can you show again that slide with the architecture of the Proto-RU?
Okay.
So to synchronize the one idea, and I wanted to check if you did that, is to synchronize the USRP using that QLSR module as a slave. So the QLSR module can act as a slave, and then it has PPS and 10 megahertz output, which you could connect to the USRP to synchronize the DU and the RU. Did you try that?
No, we just followed the very straight path like this. Connect both the PTP. So we have the network interface card on both the machines, on the DU and the RU, and then we just simply provide the signal to both.
So what is that blue line between the QLSR and the USRP then?
Yeah, I mean, like we also synchronize the RU with the QLSR also, right?
Yeah, so using the reference, the 10 megahertz reference.
10 megahertz reference.
Okay, so you did that. Okay. Okay, thanks.
Yes. Can we take one more? Yeah. Thank you.
Hi. I'm very interested in this NI channel emulator, the chess one. So just to understand the channel emulator itself, it's a packet-based channel emulator, or it's something that you do below the physical layer? Because, for example, when I say packet-based, it means like, okay, you just delay the packets and maybe some impairments such as packet loss, for example, or it's more complicated than that?
So what we try to basically do is like we have different type of channel models from the 3GPP, right? And we try to simulate those channel models inside the Shiona, and when we take the channel impulse response from the Shiona, and then we provide those channel impulse response into the chess, and through there we basically emulate the whole channel. How does it look like for the LEO satellite or for the GEO satellite? And then we provide the delay Dopplers. Then you can basically configure your TDL, the tap delay line model inside the chess by the different delay and Doppler values. And then the physical layer basically comes from the OAI side. So if I can show you one, like if you see this particular thing, so you see at the bottom there is where the physical layer communication is going on between the OAI G node B and OAI UE, right? And all the RF samples that are going outside from the USRP, they get to the channel emulator. They get exposed to all the delay and the Doppler that we have simulated, and then the UE receives those things. So we are basically emulating the satellite environment by using the chess.
So the chess is a feeder link channel emulator or surface link channel emulator or both? So because I'm confused with the exact graphic. Like, so you're trying to simulate the base station in the space?
No, we are not trying to simulate the base station in the space. It's a transparent type of a payload where everything is on the ground,
okay.
And then it's just a feeder link which you transmit. It's just a relay for you.
Okay, understood. Yeah.
Yeah.
Okay, thank you.
Okay, thank you for the time. Yeah, thank you.